All right. In this second recording of section 3C, we're going to continue our discussion in matrices. And we're going to focus on the matrix multiplication in this recording. And usually, I think in a linear algebra textbook, a lot of times, right? So we define the matrix multiplication by, probably first saying, well, if you have a matrix times a vector, that means you use those entries in the vector, make a linear combination of the columns of the matrices to form a new vector, and then go on from there. You can define this matrix m by n, then times another n by p matrix, right? So then, that's not bad. I mean, that's a very reasonable approach for a linear algebra class. But here in this book, actually, our question or the perspective for introducing the matrix multiplication is by looking at, well, if we have the product of two linear maps, if we want to represent that by using a matrix, then what is this resulting matrix in terms of the matrices of the each linear maps? Right? And in order, naturally, we may want to ask the matrix of the product ST, or two linear maps, is equal to the matrix of M times the matrix of T. And in order to make that happen, then what is our requirement on how to construct those matrices, how to construct the multiplications between the matrix M and between the matrix M of S and the matrix M of T. And then from there, we actually say, well, in order to make that relationship happen, then we need this definition as the multiplication of matrices. I think that's a very good approach, because once we introduce the matrix multiplication that way, then a lot of properties we already established on the linear maps can be just applied to the properties for the matrices multiplications. For instance, we know if there are three linear maps multiplied together, you can associate with any way you want. And then if that is the case, then that also tells us you can associate the product of matrices. All right, so then instead of going through like a elementary proof using all those elements in matrices, and we can actually use the properties for the linear maps to do some properties for the matrix multiplications. That's an advantage for this type of approach. All right, so let's get started. So we're going to look at the motivation first. All right, I'm going to introduce some notation here. So let's try to introduce three vector spaces, U, V, and W. All right? And let's consider the T, the linear map T, takes the vectors in V to the vector space W. And then another linear map S takes vectors in U to V. And so when you have the T times S, that is well defined. I remember T times S is basically the composition of T of S. All right, that's earlier section. I think probably 3.1, right? When we talk 3A, when we talk about linear maps, we define the multiplication. All right. So in this case, the TS is well defined, or ST, well, probably not, unless there are some other spaces equal to each other, right? But generally speaking, T times S is okay. And then let's consider in the metric, in the vector space U, there U1 up to UP, this is the basis. All right. And then the basis in V is V sub 1 up to V sub n, and the basis of W is W sub 1 up to W sub m. All right. So this is the three bases, three vector spaces, and then two linear maps. All right. So then observe that, in this case, TS. All right. So here where the S belonging to a linear map from U to V, and the T belonging to a linear map from the V to W. All right. And observe that TS is a linear map from U to W. Okay, so the question for us is, well, whenever we have a linear map, of course, we assume all those are finite dimensional vector spaces. So then the question is, with this new linear map, there is a matrix associated with it. So there is a matrix of this new linear map, TS. Then the question is this one actually equal to the matrix of T times the matrix of S? And maybe another way to say this is, how could we make this happen? Is there any way you can, because right now actually we do not even have the definition of what is the multiplication among the two matrices, right? So then the question is, how do we interpret this right-hand side when you write down the MT and the MS together, right? What is that? All right. So then let's consider with our basic definitions there, we're going to establish this definition of the matrix multiplication using the basic definition of M, where the M matrix is defined. All right. So remember that when we have a T here, you can find a matrix. All right. So then let's write this A11 up to A1n and AM1 up to AMN. So we're not randomly using the M and the N here, right? Because if you look at the T here is from V to W, and we said there the V, the dimension is N, right? So it's V1 up to Vn, and the W, the dimension is M, is W sub 1 to W sub M, right? And then recall, like in the first recording of this section 3C, we said if you have something from R3 to R5, that is 5 by 3, right? If you have something from R5 to R3, it's 3 by 5, all right? So that's the same idea. This is M by N matrix, all right? So that's MT. And then the other one, the MS, well, if you look at S, this is from U1 up to UP, the dimension is P for the vector space U, to the V is V1 up to Vn. Again, the dimension is N here. So this is a N by P matrix. So we're going to use, I think I'm going to use the B here. So this is a B11 up to B1P, and then this is the BN1 up to BNP. So this is a N by P matrix, N by P matrix. All right, very good. So now let's put this together to think for an K, all right, from 1 to P, right, because we look at how this composed vector, because the T, remember TS is from U to W, all right? Maybe I should put here the TS is from U to W. So we look at, well, then that matrix associated with T times S must be, you write down each basis vector in U, and then write that as a linear combination of W. And then those coefficients will define the matrix of this M of T times S. All right, so that's our idea. So that's why for each K here, we have the TS, right, of this U sub K is T. Well, so what is the U sub K here, right? Well, for the U sub K, well, the S will take the U to W. So in other words, your resulting S will take U to, S will take U to V, right? So then, yeah, let me write here. Otherwise, it's going to be confusing here. So S will take the U to the V there. So S of UK will be something in the vector space V. And the vector space V, the basis is the V there, right? It's the V there. So we can write this as the T. You can write S of U as the sigma. Let me put something like R maybe here, R from 1 to N. some kind of anything in the vector space V there, we can write this as BRK times V sub R. Sub R here. Okay, I think we're good because S of U, I remember T is, probably putting the same space here, same page here. T is from V to W, and S is from U to V there, right? So then if you have a U here, the S will take this to the V, and by our definition, right, there's a matrix associate. This matrix is MT, we can see here, this matrix MS here, right? By the definition of MS, that means if you have a U here, you take it to the V, and then each column here is the weight associated with that linear combination, those scalars, right? And then this is the case column, because this is the U sub K here. So that will be the case column along the matrix MS, and we use the letters B there, right? So that's why this is the case column. So this K is kind of fixed, and the K is from anywhere between the 1 and the P here. So what you do is you let the first subscript change, right? R from 1 to N, because this is a B1 up to Bn here, right, for each column. So it's N by P, right? So R from 1 to N, and then we have a V of R there. All right, so that is our, so this step we use by the definition of the MS. So that's what we used here. Okay, good. And then, well, the T obviously is a linear operator, so we can further distribute the T to, all those scalars can be keep out, and then we can have the T of V sub R, right, for and put the sigma notation first, all right, because this is a T of a finite sum, so it's T applied on each term of the sum, and then those B values are the scalars you can pull out in front of T, so it's just this B coefficients times the T of V sub R. All right, and what is the V sub R, right? So the V here is the T will take a V to the W, right? So if you consider what the V sub R is, well, then that V sub R, you're going to use the column R in that W, in this MT matrix here to match with the basis in the W space. All right, that's by our definition of the, all right, so this is by the definition of M of T here. So you have BR comma K here, and then this T of VR is a sigma J from 1 to M, and then we have the A, that's the MT, the numbers is A, JR, so the R's column here, and then W sub J, so the J change, and then there M by N, so if you look at MT here, it's M by N, so there M weights here on each column, M entries along each column, like M, 1R, 2R, and 3R up to MR. That's what we are talking about. A1R, A2R, and up to the AMR here, right? So now, if we put the sigma notation together, because the BRK has no summation of M here, no summation index M there. So when the J here, so when J change, this now change. So you can just put this as a constant after the second sigma notation. So we have the sigma R from 1 to N, sigma J from 1 to M, and then we can put this like A JR and BRK and WJ, and then let's switch the order of summation here. All right, so we're going to do the J first. So J from 1 to M, and then we're going to add the terms containing the subscript R first. all right, and then keep the wj. All right. So in other words, at first you have a double sum, or there are a lot of terms, but then you're thinking, well, let's fix the, for each j fixed, like 1, 2, 3 up to m, then let's look at when that ajk, when the j fixed, all right, and then a jr there, when the j fixed, let's only look at the r change, and then that's going to match with the brk when you, and of course when the j fixed, then the wj, that j is also fixed, right? So you kind of multiply the a and the b together, add them together, and then that become each sigma is one number in front of each wj, and then you let this j from 1 to m, right? So it's some number times w1 plus another number times w2 up to the last number times wm. All right. So that's what we're saying here. All right. So then what this tells us is, well, if this happens, then if we can define the MST in this fashion, then this is the M by P matrix whose entry in row J, so this is a row J here, and column K equals the sigma r from 1 to n ajr times brk. All right. Why this is that? Let's make it smaller, take another look before we move on. All right, because this one, the notation is there are many different letters we're using here, right? So, but if you think about this, is, well, we are saying we find a matrix to represent the t times s, and the t times s, as we can see from the corner here, is from the u to the v there, to the w there, right? So that means by our definition of a matrix associated with the linear map, we want to look at for each basis vector in the u1, u2, how do you write that as a linear combination of w? And then those numbers, those weights in front of those w vectors that make a column in your matrix M of t times s. All right, so that's our original definition there. So our work is this, right? So by the combination, we first apply the S on the U sub k. So we realize S U sub k, well, then you can use this matrix MS, or S from U to V, use that matrix MS to do something. And then we apply the T on the V vectors, and then you realize the T is from the V to W. So you can write the vectors T of V in terms of a combination of W using the MT. So that's where this comes from. And then we rearrange the terms by switching the sigma notation. Because remember, the goal is to write as a linear combination of W, right? So that's what we end up here as well. So here is a linear combination of W, and each one in front of W is that. So then each of this sigma notation in the pair of parentheses is going to be along the column, right? And along which column? Along the case column, because this is a U sub k. All right. So remember the coefficient associated with the U1, if you have something W together give you U1, that's the first column. All those W give you U2 is the second column, and so on. So then this TS of UK is in the case column. And that case column, well, then how many rows you have? Well, how many rows you have is the first row up to the mth row there, right? So then, in general speaking, this is the let's see what should look at it. Yeah, this is the jth row, j from 1 to m. Oh yeah, because I was confusing myself a little bit. I was looking at this whole thing, right? But we're looking at only this number in the pair of parentheses. That is the j here. All right, that's the j here, yes. All right, because when this is a w, when j is 1, w1, then that is your first one in that case column. When j is 2, that is the second one in the case column. And when j is j, that's the jth one in the case column. All right, so that is defined by this sigma notation between the A and B, the products of A and B. Right. So then that's lead us to the definition of the matrix multiplication, right? So because you originally you have T, there's a matrix MT. You have S, there's a matrix MS. So when you multiply this together, in order to make the MT times MS equal to this new matrix M of TS, so this is how we define this new matrix. Then obviously we need to come up with a way when you finish that multiplication, then each JS row case column, that entry is exactly equal to this sigma notation. All right. So then that is how we define. So this is also how we define the matrix multiplication. So let's make a remark here. All right. So then this tells us we define the product of two matrices only when the number, first the dimension need to be matched, right? Only when the number of the columns of the first matrix equals the number of rows of the second matrix. And that can be seen by our assumption. One is M by N, the other one is N by P, right? So this number of the columns N in the first matrix equal to the N by P, the number of the columns, number of the rows in the second matrix. So we definitely need a dimension match. And then after that, then we define, then this matrix, if you have the matrix A11 up to A1N, should be better. So if you have the A11 up to A1N, or AM1 times AMN, or AMN, right? So then we define this times, so this M by N matrix, and then B11 up to B1 P, BN1 up to BNP. So this, so when you finish, you get something, let's call this a C here, C1P. And then this is the CM1 up to CMP. Okay, so this is M by P matrix, where this C, I think we said the JS row, the case column is equal to the I think what letter we use there is trying to say R here, okay, AJR, and times BRK, for R from 1 to N, for R from 1 to N, okay. And where this is for, let's say we can have the J from 1 to M, and we can have the K from 1 to P. Okay, so this is how we, so this is actually how we define the matrix multiplication or the matrix product, right? So when you finish, you take the JS row of the matrix A times the case column of the matrix B, and that give you the J case entry in the resulting product matrix. And so how many numbers here in the JS row of A? Well, A is M by N, so there are N entries, right? How many numbers in the case column of B? well, then the B is N by P. So if you fix the column, then it's B, B1K, B2K up to BNK. So it's also N entries. So then they're same numbers. So you basically sum up this N numbers, give you N products, A times B something, and you add this up, you get one number. That one number is just one entry in the resulting matrix. And then this way guarantee, by our analysis on the first page and this definition on the second page, this way guarantee that the M, because remember this is your, what is this? This is also your matrix of, so the S or the T there, A is associated with T here, right? So yeah, A is associated with T here, right? So then this one here is the matrix of T. This one here is the matrix of S. And this one, by our discussion on the first page, if you define it in this fashion, then this one must be the matrix of T times S. We use the definition to prove that need to be this. All right, so in other words, when you multiply the three matrices, then the corresponding the vector T and S they multiply together, then this is the representation of that new linear map and equal to the matrix of these two given linear maps. All right, so then that's everything worked harmonically all together. All right, so that's what we want to say here. So at the end, let's do just a quick example. I think everyone probably already know, like in terms of the algebra here, how we multiply the matrices. All right, so I'm not worried too much about that. Just throwing an example here, so to make the content itself content. All right, but I think the most important thing is to understand this definition is more from a perspective of representing the linear maps using the matrices. All right, so then like this one, this is 3 by 2, and then this one is 2 by 4. So when we finish, hopefully we have a 3 by 4 matrix. All right. So the 2 kind of just make sure that all the definition matches. So then the way you do this is you take the 1 times 6 plus 2 times 2. So that's a 10. All right. So this is the first row of A times the first row column of B. So that gives you the 1, 1 position. All right, and then the first row 1, 2 times the second row 5, 1, then that gives you a 1, 2 position. So that is 7. All right, because 1, 5 is 5, 2, 1 is 2, 7. And then I will just write out the other numbers, or everyone can help me verify all those numbers calculated correctly. All right, so this will be a quick exercise or example to help you are familiar with the definition or review the definition of matrix multiplication. All right, so then by, I think, introducing this one, we finish the recording of this section 3C here. In the old edition, actually there's a little additional stuff, like talk about how you write a matrix corresponding to a vector, and then the matrix times the vector, then that is corresponding to, I think that is the thing saying, well, the matrix of the T times the acting on the vector is the same as the matrix of operator linear map T times the matrix of that vector. All right, so it's but if you think the vector is just, generally speaking, a one column matrix, then that is just a special case of what we've been talking here for any product of two matrices. All right, so we will probably right now skip that part. It's not including the second edition. Maybe that will happen later. Maybe we don't need that at all. We'll see. If we need that later, we can include that. All right, so I think this is a natural place to stop the recording for the section 3C. All right, so make sure you watch both recordings and read the books. All right, so then this concluded the discussion of the third section in chapter 3, and then we still have a few more about like how we find the inverse and how about the quotient spaces. There's a couple of other things down the road. See you in the future recordings. Thank you.